Hassium is a chemical element with symbol Hs and atomic number 108, named after the German state of Hesse. It is a synthetic element and radioactive. The most stable known isotope, 269 Hs, has a half-life of approximately 9.7 seconds, although an unconfirmed metastable state, 277 mHs, may have a longer half-life of about 130 seconds. More than 100 atoms of Hassium have been synthesized to date. In the periodic table of the elements, it is a D-block transactinide element. It is a member of the 7th period and belongs to the group 8 elements. Chemistry experiments have confirmed that Hassium behaves as the heavier homologue to osmium in group 8. The chemical properties of Hassium are characterized only partly, but they compare well with the chemistry of the other group 8 elements. In bulk quantities, Hassium is expected to be a silvery metal that reacts readily with oxygen in the air, forming a volatile tetroxide. History: the synthesis of element 108 was first attempted in 1978 by a Russian research team led by Yuri Oganessian and Vladimir Uchyonkov at the Joint Institute for Nuclear Research in Dubna, using reactions that would generate the isotopes Hassium-270 and Hassium-264. The data was uncertain and they carried out new experiments on Hassium 5 years later, where these two isotopes as well as Hassium-263 were produced. The Hassium-264 experiment was repeated again and confirmed in 1984. Hassium was officially discovered in 1984 by a German research team led by Peter Armbruster and Gottfried Munzenberg at the Institute for Heavy Ion Research in Darmstadt. The team bombarded a target of Lead-208 with accelerated nuclei of iron-58 to produce 3 atoms of the isotope Hassium-265. Due to this issue, a controversy arose over who should be recognized as the official discoverer of the element. The IUPAC Transfermium Working Group recognized the GSI collaboration as official discoveries in the 1992 report. They stated that the GSI collaboration was more detailed and, of itself, carries conviction, and that while the combined data from Dubna and Darmstadt confirmed that Hassium had been synthesized, the major credit was awarded to the GSI. This statement came in spite of the combined data also supporting the Russian 1983 discovery claim and the TWG also acknowledging that very probably element 108 played a role in the Dubna experiment. The name Hassium was proposed by Peter Armbruster and his colleagues, the officially recognized German discoverers, in 1992, derived from the Latin name for the German state of Hesse where the institute is located. Using Mendeleev's nomenclature for unnamed and undiscovered elements, Hassium should be known as osmium. In 1979, during the Transfermium Wars, IUPAC published recommendations according to which the element was to be called unloxium. A systematic element name as a placeholder until the element was discovered and a permanent name was decided on. Although widely used in the chemical community on all levels, from chemistry classrooms to advanced textbooks, the recommendations were mostly ignored among scientists in the field, who either called it element 108 with the symbol of or even simply 108, or used the proposed name Hassium. In 1994 a committee of IUPAC recommended that element 108 be named Hahnium after the German physicist Otto Hahn, after an older suggestion of Otto Hahnium in spite of the long-standing convention to give the discoverer the right to suggest a name, so that elements named after Hahn and Lise Meitner would be next to each other, honoring the joint discovery of nuclear fission. This was because they felt that Hesse did not merit an element being named after it. After protests from the German discoverers and the American Chemical Society, IUPAC relented and the name Hassium was adopted internationally in 1997. Natural occurrence. Hassium is not known to occur naturally on Earth. The half-lives of all its known isotopes are short enough that no primordial Hassium would have survived to the present day. This does not rule out the possibility of unknown longer-lived isotopes and nuclear isomers existing, some of which could still exist in trace quantities today if they are long-lived enough. In the early 1960s, it was predicted that long-lived deformed isomers of Hassium might occur naturally on Earth in trace quantities. This was theorized in order to explain the extreme radiation damage in some minerals that could not have been caused by any known natural radioisotopes, but could have been caused by super-heavy elements. In 1963, Soviet scientist Viktor Chertynzev, who had previously claimed the existence of primordial curium-247, claimed to have discovered element 108 in natural molybdenite and suggested the name selenium for it, after the ancient city of Sarak along the Silk Road in Kazakhstan where his molybdenite samples came from. His rationale for claiming that selenium was the heavier homologue to osmium was that minerals supposedly containing selenium formed volatile oxides when boiled in nitric acid, similarly to osmium. His findings were criticized by V.M. Kulokov on the grounds that some of the properties Chertynzev claimed selenium had were inconsistent with the then-current nuclear physics. The chief questions raised by Kulokov were that the claimed alpha decay energy of selenium was many orders of magnitude lower than expected, and the half-life given was 8 orders of magnitude shorter than what would be predicted for a nuclide alpha decaying with the claimed decay energy. But at the same time, a corrected half-life in the region of 1016 years would be impossible, as it would imply that the samples contained about 100 milligrams of selenium. In 2003, it was suggested that the observed alpha decay with energy 4.5 MeV could be due to a low energy and strongly enhanced transition between different hyperdeformed states of a Hassium isotope around 271 H's, thus suggesting that the existence of super-heavy elements in nature was at least possible, although unlikely. In 2004, the Joint Institute for Nuclear Research conducted a search for natural Hassium. This was done underground to avoid interference and false positives from cosmic rays, but no results have been released, strongly implying that no natural Hassium was found. The possible extent of primordial Hassium on Earth is uncertain. It might now only exist in traces, or could even have completely decayed by now after having caused the radiation damage long ago. In 2006, it was hypothesized that an isomer of 271 H's might have a half-life of around times 108 Y, which would explain the observation of alpha particles with energies of around 4.4 MeV in some samples of molybdenite and osmiridium. This isomer of 271 H's could be produced from the beta decay of 271 BH and 271 Sg, which, being homologous to rhenium and molybdenum respectively, should occur in molybdenite along with rhenium and molybdenum if they occurred in nature. Since Hassium is homologous to osmium, it should also occur along with osmium in osmiridium if it occurred in nature. The decay chains of 271 BH and 271 Sg are very hypothetical, and the predicted half-life of this hypothetical Hassium isomer is not long enough for any sufficient quantity to remain on Earth. It is possible that more 271 H's may be deposited on the Earth as as the Solar System travels through the spiral arms of the Milky Way, which would also explain excesses of plutonium-239 found on the floors of the Pacific Ocean and the Gulf of Finland. But minerals enriched with 271 H's are predicted to also have excesses of uranium-235 and lead-207, and would have different proportions of elements that are formed during spontaneous fission, such as krypton, zirconium, and xenon. Thus, the occurrence of Hassium in nature in minerals such as molybdenite and osmiride is theoretically possible, but highly unlikely. Isotopes. Hassium has no stable and naturally occurring isotopes. Several radioactive isotopes have been synthesized in the laboratory, either by fusing two atoms or by observing the decay of heavier elements. 12 different isotopes have been reported with atomic masses from 263 to 277, 4 of which Hassium-265, Hassium-267, Hassium-269, and Hassium-277 have known metastable states. Most of these decay predominantly through alpha decay, but some also undergo spontaneous fission. The lightest isotopes, which usually have shorter half-lives, were synthesized by direct fusion between two lighter nuclei and as decay products. The heaviest isotope produced by direct fusion is 271 H's. Heavier isotopes have only been observed as decay products of elements with larger atomic numbers. In 1999, American scientists at the University of California, Berkeley, announced that they had succeeded in synthesizing 3 atoms of 293,118. These parent nuclei were reported to have successively emitted 3 alpha particles to form Hassium-273 nuclei, which were claimed to have undergone an alpha decay, emitting alpha particles with decay energies of 9.78 and 9.47 MeV and half-life 1.2 s, but their claim was retracted in 2001. The isotope was successfully produced in 2010 by the same team. The new data matched the previous data, 270 H's, prospects for a deformed doubly magic nucleus. According to calculations, 108 is a proton magic number for deformed nuclei, and 162 is a neutron magic number for deformed nuclei. This means that such nuclei are permanently deformed in the ground state but have high, narrow fission barriers to further deformation and hence relatively long lifetimes to spontaneous fission. The spontaneous fission half-lives in this region are typically reduced by a factor of 109 in comparison with those in the vicinity of the spherical, doubly magic nucleus 298 FL, caused by the narrower fission barrier for such deformed nuclei. Hence, the nucleus 270 H's has promise as a deformed doubly magic nucleus. Experimental data from the decay of the darmstadtium isotopes 271Ds and 273Ds provides strong evidence for the magic nature of the N equals 162 subshell. A recent synthesis of 269 H's, 270 H's, and 271 H's also fully support the assignment of N equals 162 as a magic number. In particular, the low decay energy for 270 H's is in complete agreement with calculations. Evidence for the magicity of the Z equals 108 proton shell can be obtained from 2 sources: the variation in the partial spontaneous fission half-lives for isotones and the large gap in the alpha-Q value for isotonic nuclei of Hassium and darmstadtium. For spontaneous fission, it is necessary to measure the half-lives for the isotonic nuclei 268 Sg, 270 Hs and 272 Ds. Since the isotopes 268 Sg and 272 Ds are not currently known, and fission of 270 Hs has not been measured, this method cannot yet be used to confirm the stabilizing nature of the Z=108 shell. Good evidence for the magicity of the Z=108 shell can nevertheless be found from the large differences in the alpha decay energies measured for 270 Hs, 271 Ds and 273 Ds. More conclusive evidence would come from the determination of the decay energy for the unknown nucleus 272 Ds. Predicted properties. Various calculations show that Hassium should be the heaviest known group 8 element consistent with the periodic law. Its properties should generally match those expected for a heavier homologue of osmium, with a few deviations arising from relativistic effects. Physical and atomic. The previous members of group 8 have relatively high melting points. Much like them, Hassium is predicted to be a solid at room temperature, although the melting point of Hassium has not been precisely calculated. Hassium should crystallize in the hexagonal close-packed structure, similarly to its lighter congener osmium. Pure metallic Hassium is calculated to have a bulk modulus comparable to that of diamond. Hassium is expected to have a bulk density of 40.7 grams per cc, the highest of any of the 118 known elements and nearly twice the density of osmium, the most dense measured element, at 22.61 grams per cc. This results from Hassium's high atomic weight, the lanthanide and actinide contractions, and relativistic effects, although production of enough Hassium to measure this quantity would be impractical, and the sample would quickly decay. Osmium is the densest element of the first 6 periods, and its heavier congener Hassium is expected to be the densest element of the first 7 periods. The atomic radius of Hassium is expected to be around 126 pm, due to the relativistic stabilization of the 7s orbital and destabilization of the 6d orbital. The Hs plus ion is predicted to have an electron configuration of 5f1465 7s2, giving up a 6d electron instead of a 7s electron, which is the opposite of the behavior of its lighter homologues. On the other hand, the Hs2 plus ion is expected to have an electron configuration of 5f1465 7s1, analogous to that calculated for the Os2 plus ion. Chemical Hassium is the 6th member of the 6d series of transition metals and is expected to be much like the platinum group metals. Calculations on its ionization potentials, atomic radius, as well as radii, orbital energies, and ground levels of its ionized states are similar to that of osmium, implying that Hassium's properties would resemble those of the other group 8 elements, iron, ruthenium, and osmium. Some of these properties were confirmed by gas phase chemistry experiments. The group 8 elements portray a wide variety of oxidation states, but ruthenium and osmium readily portray the group oxidation state of +8, and this state becomes more stable as the group is descended. Thus, Hassium is expected to form a stable +8 state. Analogously to its lighter congeners, Hassium is expected to also show other stable lower oxidation states, such as +6, +5, +4, +3, and +2. Indeed, Hassium is expected to be more stable than Hassium in aqueous solution. The group 8 elements show a very distinctive oxide chemistry which allows extrapolations to be made easily for Hassium. All the lighter members have known hypothetical tetroxides, MO4. Their oxidizing power decreases as one descends the group. Ionate oxide is not known due to its extraordinarily large electron affinity, which results in the formation of the well-known oxoanion ferric iron 2 peroxide -4. Ruthenium tetroxide RuO4, formed by oxidation of ruthenium in acid, readily undergoes reduction to ruthenate RuO2-4. Oxidation of ruthenium metal in air forms the dioxide RuO2. In contrast, osmium burns to form the stable tetroxide OSO4, which complexes with the hydroxide ion to form an osmium-8 complex 2-. Therefore, eco-osmium properties for Hassium should be demonstrated by the formation of a stable, very volatile tetroxide HSO4, which undergoes complexation with hydroxide to form a Hesse-It 2-. Ruthenium tetroxide and osmium tetroxide are both volatile. Due to the symmetrical tetrahedral molecular geometry and the being charge-neutral, Hassium tetroxide should similarly be a very volatile solid. The trend of the volatilities of the group 8 tetroxides is known to be RuO4 and LtOSO4 and GtHSO4, which completely confirms the calculated results. In particular, the calculated enthalpies of adsorption of HSO4 -kJ-mol-1 on quartz agrees very well with the experimental value of -kJ-mol-1. Experimental chemistry. Despite the fact that the selection of a volatile Hassium compound for gas phase chemical studies was clear from the beginning, the chemical characterization of Hassium was considered a difficult task for a long time. Although Hassium isotopes were first synthesized in 1984, it was not until 1996 that a Hassium isotope long-lived enough to allow chemical studies to be performed was synthesized. Unfortunately, this Hassium isotope, 269Hs, was then synthesized indirectly from the decay of 277Cn. Not only are indirect synthesis methods not favorable for chemical studies, but also the reaction that produced the isotope 277Cn had a low yield, and thus did not provide enough Hassium atoms for a chemical investigation. The direct synthesis of 269Hs and 270Hs in the reaction 248Cm 274-XHS appeared more promising, as the cross-section for this reaction was somewhat larger, at 7 pb. This yield was still around 10 times lower than that for the reaction used for the chemical characterization of bohrium. New techniques for irradiation, separation, and detection had to be introduced before Hassium could be successfully characterized chemically as a typical member of Group 8 in early 2001. Ruthenium and osmium have very similar chemistry due to the lanthanide contraction, but iron shows some differences from them. For example, although ruthenium and osmium form stable tetroxides in which the metal is in the +8 oxidation state, iron does not. Consequently, in preparation for the chemical characterization of Hassium, research is focused on ruthenium and osmium rather than iron, as Hassium was expected to also be similar to ruthenium and osmium due to the actinide contraction. Nevertheless, in the planned experiment to study Hesse-It, ferrocene may also be used for comparison along with ruthenocene and osmocene. The first chemistry experiments were performed using gas thermochromatography in 2001, using 172 Os and 173 Os as a reference. During the experiment, 5 Hassium atoms were synthesized using the reaction 248 Cm 269Hs. They were then thermalized and oxidized in a mixture of helium and oxygen gas to form the tetroxide oxide, 269 Hs plus 2O2, 269 HSO4. The measured deposition temperature indicated that Hassium oxide is less volatile than osmium tetroxide, OSO4, and places Hassium firmly in group 8. However, the enthalpy of adsorption for HSO4 measured kJ per mole was significantly lower than what was predicted, kJ per mole, indicating that OSO4 was more volatile than HSO4, contradicting earlier calculations, which implied that they should have very similar volatilities. For comparison, the value for OSO4 is kJ per mole. It is possible that Hassium tetroxide interacts differently with the different chemicals used for the detector. Further research is required, including more accurate measurements of the nuclear properties of 269 Hs and comparisons with RuO4 in addition to OSO4. In 2004, scientists reacted Hassium tetroxide and sodium hydroxide to form sodium Hesse.It, a reaction well known with osmium. This was the first acid-base reaction with a Hassium compound, forming sodium Hesse.It, HSO4 plus 2 sodium hydroxide Na, 2 HSO2. The team from the University of Mainz are planning to study the electrodeposition of Hassium atoms using the new Tasker facility at the GSI. The current aim is to use the reaction 226 Ra 270 Hs. In addition, scientists at the GSI are hoping to utilize Tasker to study the synthesis and properties of the Hassium compound Hessicine, Hs2, using the reaction 226 Ra. This compound is analogous to the lighter ferrocene, radonocene, and osmocene, and is expected to have the two cyclopentadienyl rings in an eclipsed conformation like radonocene and osmocene, and not in a staggered conformation like ferrocene. Hessicine was chosen because it has Hassium in the low formal oxidation state of +2 rather than the high +8 state which had previously been investigated, and relativistic effects were expected to be stronger in the lower oxidation state. Many metals in the periodic table for metallocenes, so that trends could be more easily determined, and the highly symmetric structure of Hessicine and its low number of atoms also make relativistic calculations easier. Hessicine should be a stable and highly volatile compound.